So other colligative properties related to vapor pressure lowering. So vapor pressure lowering occurs at all temperatures. That means that the temperature required to boil the solution is higher than the boiling point of the pure solvent, right? Because if you go up to the boiling temperature in that solution, the vapor pressure is lower. It's not going to boil at that atmospheric pressure. You have to heat it up higher so that the vapor pressure of the solution is equal to the vapor pressure, is equal to atmospheric pressure, is equal to vapor pressure that you would have seen at the boiling point of a pure solution. It turns out that if you're, for the same sorts of reasons, that the temperature required to freeze the solution is lower than the freezing point of the pure solvent. By basically the same dynamic equilibrium arguments, that you have an equilibrium between molecules leaving the solution to crystallize onto your solid, and the solid going back into solution. And again, you have a pure solid. You haven't changed the rate that molecules go onto this, that molecules come off the solid, but you have changed the rate at which molecules go from the solvent onto the solid. So you lower the freezing point as well, because you've changed that dynamic equilibrium to favor the liquid phase, which is the solution phase. Yeah, so what you get if you look at the chart like this, then if you look at, here we've got pressure on the y-axis and temperature on this axis, and you have a phase diagram with pure solvent. In solution, what you'll be doing is making the liquid more stable. So it will freeze at a lower temperature, and it will boil at a higher temperature. And this is, you're expanding the region that the liquid is stable in. And so basically liquids are stabilized with respect to gas and solids because the liquids are solutions and are mixtures. Whereas, the vapor, the solids are, is not, the vapors are not. So because of that mixtures is why you stabilize the, liquid solution. So this is very useful. Antifreeze. Antifreeze helps both to prevent the water from boiling off, but also prevent it from the liquid in your car from freezing at low temperatures. So quite useful. You don't want any sort of water in the internals of the engine freezing at 30 degrees. You want to use antifreeze to push that down quite a lot. So yeah, freezing point depression. The freezing point of a solution is lower than the freezing point of the pure solvent. Therefore, the melting point of the solid solution, is lower. And the difference between the freezing point of the solution and the freezing point of the pure solvent is directly proportional to the molar concentration of solute particles. And so here we use molal. Here we could use another concentration, but because we're looking at temperature dependent properties and they're relatively small, it's easier to tabulate everything in terms of molalities. So this proportionality constant is called the freezing point depression constant. And of course, the value depends on the solvent. It doesn't depend particularly on the solute, it depends on the solvent, right? Because it has to do with the concentration of the solvent. And so the units are, of course, going to be degrees per molal. So an exact parallel with the freezing point depression, the boiling point elevation with a non-volatile solute is higher than the boiling point of the pure solvent. The difference, again, it's proportional to the molal concentration of the solute particles, because that's related to the concentration of the solvent. Remember, our deltas, when we have a delta, that's related to the concentration of the solute. If we were to just look at the boiling point of the solvent, this would be proportional to the mole fraction. But because we're looking at the difference that the boiling point changes, we're multiplying by a solute dependent quantity, because that'll be proportional to 1 minus solute concentration. Okay, so again, this proportionality constant is the boiling point elevation constant. You could do everything in terms of molarity as well, but by changing the way you do the units, but it's more consistent to do it in terms of molalities because you're looking at temperature changes, and the molality does not change as the temperature changes. Again, of course, this constant depends on the solvent. The units are the same for freezing point. So let's look at a little of these freezing point, depression, and boiling point elevation constants. You can see some trends here. Usually the freezing point constant is large. The freezing point depression is larger than the boiling point elevation for the same amount of solute. And that generally, if one is large, this is relatively large, this is relatively large as well. Water has a relatively small freezing point constant and a relatively small boiling constant as well. And actually, you have to put a lot of stuff in to raise the boiling point of water compared to some other fluids. So in a lot of this, it all depends on sort of the solute interactions. It's there's a lot of details going on there. What we can say is, we know roughly that it's going to be have a linear constant of proportionality. So conceptual question now. Solvent A is a 1 molar solution with a non-ionic solute and water as the solvent. Solute B is a 1.0 molar molal solution. Sorry, I slipped. With the same non-ionic solute and ethanol as the solvent. Which solution has the greater increase in the boiling point relative to the pure solvent? And conceptually, what we see is that the ethanol has a larger boiling point constant. So with the same amount of solute, lowering the concentration of the solvent by the same amount, its boiling point is changed more. So the answer will be solution B. Ethanol is more affected by a change in the concentration of the solvent, which we tabulate in terms of the amount of solute.